To better understand the properties of the predict random effects, let us now consider the prediction of random effects in the variance component model. And recall that the variance component model was the most simple possible mixed effect model, where the fixed part includes only the common mean of group means, the random effect. There is only one random effect per group, random intercept, and then there is the residual error epsilon aj. And we can write the model for a single group in this form, where this 1 here is the vector, is the column vector specified here. So it has a total of ni rows and 1 column, and all elements of the matrix or the vector are ones. And in this model, the only fixed effect is this mu, and we denote it by mu instead of the beta, just to emphasize that this is the estimated marginal mean over the groups, a marginal expected value of yi over the groups. And we can write this model also in the marginal form in this way. So now we are assuming that this ei vector includes both the random effects and the residual errors. And in this marginal model, the variance of the residual term ei, which we denote by wi here, it can be written in this form: sigma squared I plus sigma squared b multiplied by j, and these I and j, I is the identity matrix and j is a matrix filled by ones. So I is a matrix that includes ones in the diagonal and zeros in the off diagonal, and the J matrix includes ones everywhere. Like this. The best linear unbiased predictor becomes, in general terms, it was written in this form, and now this matrix here is this W matrix here, and therefore this becomes more simple than in the general form, and we can also write this expected value vector in this form. And we can also write this term here as sigma squared b multiplied by 1 prime, just by definition of the Z matrix for this particular group. Oh, I'm sorry, I'm missing the indices from here, all matrices. It can be shown that this Wi matrix, the inverse of the Wi matrix, can be written in this kind of compact form. The proof is not shown here, but it is left as an exercise. And therefore we can write this expression in the place of this inverse here. So the best linear unbiased predictor of the random effects gets this form, and now we can simplify this. First we can take the sigma squared from the denominator here in the front of the expression, and so the first term that remains is just the 1 matrix prime multiplied by the identity matrix, and then for the second term here we can take this fixed scalar in the front of the expression, and therefore this 1 prime matrix can be written in this part or this place here in the between of the scalar multiplier and J matrix, like this, and then we still have this last term like this, and then this part here is directly 1 prime, so multiplying 1 prime by the identity matrix has no effect, and then what happens to this part here, we can write this as ni, and then this 1 prime. And then we can also take this 1 prime here and here as a common term and move, and it goes to this part of the expression. And now our formula looks like this. Then we can simplify the first 2 terms in the product like this. And now we see that in the numerator, so what we just did, we expanded this number 1 as a product sigma squared plus ni sigma squared b per sigma squared plus ni sigma squared b. And now in the numerator we have terms that cancel out, and then we also these terms cancel out. So the only thing that is left in the numerator is the sigma squared b from the first term, and in the denominator we have the term that is shown here. And then what happens here, we have not yet written it here, so 1 prime y is just the sum of yi, and also 1 prime multiplied by mu 1 is just a sum of mu n times, so it's just n mu. So this last term comes like this. And now for convenience we divide both terms by n and multiply everything by n. So then we can take this n to this expression here, and actually these n's cancel out, and this sigma yi per n is now here it is just the y bar. So the formula gets this form. Okay, what do we see from this expression? First we see that the term here is just the y bar, the sample mean of that particular group minus the grand mean or expected grand mean over all groups, so mean of group specific means, and the random effect vi is obtained by multiplying this difference by something. And now if we look at this expression, we see that this is ni sigma squared b divided by something where we have ni sigma squared b plus sigma squared. So the numerator is higher than the denominator is higher than the numerator, so therefore this value here is bounded to be between 0 and 1. So therefore, that means that the random effect is always between 0 and the difference between the group mean and the population mean mu. So let us consider the case where we have only one observation in group I, so ni is 1. Then we get our expression becomes quite simple, very simple. And then if we want to compute the group mean in that group, then the group mean is the random effect, is the fixed mean plus the random effect. We denote the group mean by this yi dot tilde. We have the tilde because it's a prediction, and yi dot, the dot means that we take mean over all j values of that particular group I, and it is mu plus bi, and we can write it in this form by just replacing beta tilde by its value or estimator or predict. Let us denote this weighting vector by wi, so now we know that it is a weight that is between 0 and 1, and now we can write this in a new form this way, and now when we simplify we get 1 minus wi multiplied by mu hat plus wi multiplied by y bar. Now we see that this estimation of the group mean is weighted mean of mu hat and y bar, and the weight is determined by the ratios, by the values of sigma squared and sigma squared b. If we have a situation where the sigma squared is 0, so where the within group variance is 0, and therefore all variability is between groups and sigma squared b is non-zero, then this weighting factor becomes sigma squared b per sigma squared b, which is 1, and it means that the random group effect is same as the group specific mean y bar, and that means that in that case it doesn't matter whether we estimate the group effect as a fixed or random, the answer is the same, or the solution, the value of that is the same. Value of the group effect and value of the group mean are the same. So yi dot tilde is equal to y bar. Then if we are in the other end, so if the residual variance is positive but the variability between groups is 0, which means that there is no dependence in the observations of the same group, then our wi is 0, and then our prediction y of the group mean is the grand mean of the population. So it means that the observed yi from that group does not include any additional information about the group mean compared to what we already know about the mean of group means from the whole data. So let us make a graphical presentation. On y-axis we have y here, and because we have a variance component model, we have actually nothing in the x-axis, but we just plot this particular group at this location here. And now the estimated mean of group means is shown by this line mu hat here, and then this yij here is the observation from this particular group in the data. If we estimated the group effect as fixed, then our estimated group mean would be this particular value here, the observed value here. But now that we have estimated the group mean as a random, then the predicted group mean for this particular group is somewhere between this observed yij and the mu hat here. And how much, we can think it two ways. So first we can think that, okay, we take the fixed group mean and shrink it towards to the population mean, or we can think that, okay, we take the population mean mu and then adjust it towards the observed yij of the group. But the question is that how much we should adjust the mu towards yij, or how much we should shrink the yij towards mu, depends on what are the values of our variances of the group effects and within group variance. So here is, in a way, or here is the difference we observe between the mean of group means and this particular observation, and then we divide this in two parts, so that the ratio of the division is based on the sigma squared and sigma squared b. And now in this graph I'm drawing it in a way that sigma squared b and sigma squared seems to be almost equal, and in this case when we have only one observation per group, then it means that our estimate for the group mean is here. Now let us again look at this bi tilde for the group where we have more than one observation. Now we also can see that this is a weighted average, or if we compute the yi dot tilde for this particular group, then we can denote this as the weight w, and again the predicted mean for the group is mu hat plus bi tilde, and we can write it in this way, where wi is here and here we have 1 minus w, and we see that actually the weights for y bar is sigma squared b per sigma squared per ni plus sigma squared b, and then sigma the weight for the y mu hat is sigma squared per ni per sigma squared per ni. And now we see that what is actually this term here. This is a well-known formula for variance of y bar, which is variance of y per n. And this means that in this variance component model, if we have more than 2 observations, we in a way can interpret that we only take the sample mean of the observations, and then assume that the within group variance in that is reduced by this formula. So if we have 2 observations, the variance within group is reduces to a half, and so on. So in a way, these several observations can be treated or thought as one single observation from that group, but then the residual variance for that is reduced according to the formula for the variance of the sample mean. Let us again illustrate it graphically. So we assume that mu hat is the line shown here, and then those 3 blue dots show 3 observations from group I, and now the mean of them is at this level. So this is our level for which is the y bar for this particular group I. And now when we estimate the random group effect, so then we divide this difference here to 2 parts, and the first part here is sigma squared per n, and then the second part is sigma squared b, in this way. And then our prediction for the random group mean would be y tilde I dot at this level. And we see from this formula that when the number of observations increases, the sigma squared n gets smaller and smaller, so therefore this term here goes to 0, and our prediction of group mean approaches this sample mean of the group y bar I. Now recall from previous weeks of the course that y bar I, the sample mean of that particular group, is our estimator of group mean if group effect is treated as fixed. Now the random group mean, according to what we have seen in this video previously, the random group mean is a weighted average of this mu hat and the fixed group mean, and the weights are depend on the number of observations and on the variances between groups and within groups. So if either n goes to infinity, so if the number of observations per group increases, or if our variance within group goes to 0, so if it's very small, variance within groups is 0, then this weight goes to 1, approaches to 1, and therefore our predicted random group mean approaches this fixed group effect. And in the other side, if when n approaches to 0, so if we don't have any observations from the group, or when the number of observations per group decreases, of this, when the number of observations from this particular group I decreases or approaches to 0, or if the variability between groups is 0, then the weight goes to 0, and our predicted group mean is equal or approaches to the estimated mean of group means over all groups.